So far, we've looked primarily at a localized electron model of bonding where we've used individual bonds and electron pair repulsions. Now we're going to look at orbitals and examine bonding in more detail, specifically how atomic orbitals rearrange when a chemical bond forms to give hybridized orbitals. Now, if we start with a free carbon atom, we know we have s and p orbitals available. However, if carbon bonded to something like hydrogen and methane through these s and p orbitals, we would have 2s and 2p orbitals for carbon, which would give two different bond types. We would have 3 carbon-hydrogen 2p1s bonds and 1 carbon-hydrogen 2s1s bond, which would be mutually perpendicular at 90 degrees. But methane is known to have 4 equivalent bonds tetrahedrally arranged, which means that our atomic orbitals must change into hybrid orbitals. We mix the native atomic orbitals to form these special orbitals for bonding. Here's our methane molecule. We know that we have 4 equivalent bond lengths and bond angles of 109.5 degrees, which means, again, that we must hybridize our orbitals. Since we start with 4 atomic orbitals, 1s and 3p orbitals, we end up with 4 equivalent sp3 hybrid orbitals. They're arranged at 109.5 degrees from one another based on our valence shell electron pair repulsion theory. The sp3 hybrid orbitals are lower in energy than the 2p orbitals, which is why they form. When we stick electrons into these sp3 hybrid orbitals, the electrons will be lower in energy than they would be if we put them into unhybridized orbitals. In sp3 hybridization, we have the combination of 1s and 3p orbitals. Notice that the superscripts 3 plus 1 equal the total number of hybrid orbitals for sp3 hybrid orbitals. Whenever a set of equivalent tetrahedral atomic orbitals is required by an atom, the localized electron model assumes the atom adopts a set of sp3 orbitals. The atom becomes sp3 hybridized. The 4 orbitals are identical in shape. The bond lengths are the same size, and the bond angles are all the same, 109.5. Here we have our central carbon atom with our sp3 orbitals shown in purple overlapping with our 1s hydrogen orbital. The electrons are shown as arrows up and down. Now when we mix an s and 2p orbitals together, we get a new type of hybrid orbital. If we look, for example, at ethylene, we have 3 groups of electrons around our carbon atoms. That requires 3 hybrid orbitals. We take an s orbital and 2p orbitals to get an sp2 hybridized orbitals. Again, since we started with 3 atomic orbitals, we get 3 hybridized orbitals. The superscripts 2 plus 1 on the type of hybrid orbital, sp2, equals 3, which is the total number of hybrid orbitals. We have a 120 degree bond angle in this trigonal planar arrangement of our sp2 hybridized orbitals. The sigma bond, the bond between the 2 carbon atoms caused by our sp2 hybridized orbital, is through the internuclear axis at 120 degrees from our sp2 orbital overlap with the 1s orbitals on hydrogen. Again, if we look at an energy diagram, our hybridized orbitals are lower in energy than our unhybridized 2p orbitals. In our sp2 hybridization, we're combining 1s and 2p orbitals to give a trigonal planar arrangement of 3 atomic orbitals at 120 degrees from one another. There's one p orbital which is not used. It's unhybridized and oriented perpendicular to the plane of the sp2 orbitals. Now our sigma bond is the electron pair shared in an area centered on a line running between the atoms. It's the bond along the internuclear axis. A pi bond forms the double and triple bonds we'll see by sharing electron pairs in a space above and below the sigma bond. It uses unhybridized p orbitals to form these pi bonds. Here we have our hybridized sp2 orbitals shown in green in the plane shown in yellow, and our unhybridized p orbital is perpendicular to that yellow plane containing our hybridized sp2 orbitals. Again, if we look back at our ethylene example, we have our sigma bond through the internuclear axis, and then our pi bond, our second bond between carbon atoms, perpendicular to that internuclear axis. Notice there are 2 lobes shown and lines drawn between both sets of lobes, but the electrons will only be in one space, either above or below the internuclear axis. Now, if we look at the complete bonding picture for ethylene, we see our sigma bond between our sp2 hybridized orbitals between carbon and hydrogen's 1s orbital, and then we see our unhybridized 2p orbitals forming the pi bond perpendicular to the internuclear axis of carbon. A third bond type can come about when we combine an s orbital and one p orbital. When we need 2 equivalent sets of hybridized orbitals, we get sp hybridization, as is shown in carbon dioxide. The sp orbitals are oriented at 180 degrees and result in a linear arrangement. We combine one s and one p orbital. Since there's 2 atomic orbitals, we get 2 hybridized orbitals. This gives the linear arrangement with 2 p orbitals not used, which can form pi bonds. This is how we get our triple bonds as well as 2 double bonds. If we look at the hybridized orbitals on carbon, our sp orbitals will overlap with the sp2 orbitals on our oxygen to give us our sigma bonds. Again, our hybridized orbitals are lower in energy than our unhybridized 2p orbitals. This still leaves 2 unhybridized p orbitals on our carbon. We also have an unhybridized p orbital on our oxygen. We get our sigma bond through the internuclear axis between our hybridized orbitals on oxygen and carbon. And then we get a pi bond between carbon and oxygen on the right through an unhybridized p orbital set, and another pi bond between carbon and oxygen on the left through an unhybridized p orbital. If we look at nitrogen, molecular nitrogen, N2, has a triple bond between the 2 nitrogens. The triple bond is formed between sp hybridized orbitals, giving the sigma bond through the internuclear axis. A lone pair is held in the other lobe of the sp hybridized orbital. The unhybridized p orbitals form the second and third bond between our nitrogens. Now let's look at a couple of atoms that we've seen to have expanded octets. In expanded octets, we need to have elements in the third period and below because these elements have available d orbitals. We need a d orbital in order to have 5 groups of electrons. We take a d plus an s plus a couple of p's, 3 to be exact here, and we get 5 dsp3 hybrid orbitals on our phosphorus. In dsp3 hybridization, we start with 5 atomic orbitals, which gives us our 5 dsp3 hybridized orbitals. This gives us the trigonal bipyramidal arrangement of 5 equivalent hybrid orbitals. Here in phosphorus pentachloride, we can see the trigonal bipyramidal arrangement of the 5 chlorines around our central phosphorus. We've also seen expanded octets on sulfur. Here we have 6 equivalent D2 sp3 orbitals giving an octahedral arrangement of hybridized orbitals around sulfur. In D2 sp3 hybridization, we combine 2 d orbitals, 1 s orbital, and 3 p orbitals to get the 6 D2 sp3 hybrid orbitals. This gives an octahedral arrangement of hybrid orbitals. And so to summarize, when we have 2 groups of electrons around a central atom, our number of effective pairs is 2. The arrangement of pairs is linear to optimize spacing. This gives us sp hybridization with a 180-degree bond angle. When there are 3 effective pairs around a central atom, we have a trigonal planar arrangement, sp2 hybridization with a 120-degree bond angle. With 4 groups around a central atom, we have a tetrahedral geometry with sp3 hybridized orbitals at 109.5 degrees from one another. With 5 groups around a central atom, we have a trigonal bipyramidal arrangement of dsp3 hybrid orbitals. The orbitals around the central part of the molecule are at 120 degrees, while the atoms at the top and bottom are at 90 degrees from the middle. With 6 groups around a central atom, we end up with D2 sp3 hybridization and octahedral geometry where all groups are 90 degrees from one another.